Okay, so in the last lecture, we were looking at the Landau-Ginsburg theory, and we showed that in the Landau-Ginsburg formulation, one can write down a Lagrangian for the system, and using the Lagrangian formulation, one can derive the mean field theory results. And we showed all the critical exponents that we had obtained using mean field theory could be reproduced using the Landau-Ginsburg description. The advantage of Landau-Ginsburg description over the mean field description was that it has a Lagrangian formulation, and the mean field was produced by assuming that the order parameter, which is the Landau-Ginsburg field itself, takes a spatially independent uniform constant value, which could of course depend on temperature, but not depend on space. And that is the kind of approximation that we did in the mean field theory. So what Landau-Ginsburg formulation shows is that if you make a uniform approximation for the order parameter, mean field theory can be reproduced using Landau-Ginsburg model. Of course, you can always go beyond that within the Landau-Ginsburg theory by allowing the field to fluctuate. And instead of taking spatially uniform profile, if we take the profile which does depend on space, then clearly a more nuanced or more detailed information can be extracted using the Landau-Ginsburg type formulation. Okay, so to understand that, what we will do is we'll try to develop the formalism a little bit and derive a new criteria, which would tell you under which circumstances the Landau-Ginsburg type of description would be suitable description for a particular system that is under study. Okay, so one of the things that we were looking at last time was studying the fluctuations of the Landau-Ginsburg field around its mean field value. Okay, and we denoted the fluctuation by just var phi, where the mean field value was phi m. And the idea was to write down the Landau-Ginsburg field phi as the spatially uniform value, mean field value, plus the fluctuation, and plug it into the Landau-Ginsburg action. And the idea was to look at terms which are at least quadratic in the fluctuation or higher powers. Okay, and which is what would have given us the action for the fluctuation. Okay, so if we concentrate on the quadratic part of the action, which are three terms, the grad phi squared term, a by 2 phi squared term, and 3g by 2 phi m squared phi squared term. And if you put all of them together, then you can check that the scalar field that the fluctuation field that one is looking at would always have the positive mass squared value, although it doesn't seem like that when one tries to write it explicitly. But for t greater than tc, the parameter a is positive, and for t less than tc, the parameter a is negative. So therefore, in both the cases, the mass squared formula is always positive. Okay. Okay, so what one could do after that, or what we did after that, was to substitute the Fourier decomposition of the fluctuations into the action and extract the quadratic part of the action by substituting this Fourier expansion, and the phi would look something like this. The quantity m squared, explicit value of that depends upon whether we are working in the phase where temperature is above critical temperature or below critical temperature, and the factor of m squared differs by 2 in that case. Okay. We of course have to impose reality conditions for the Fourier modes because the fluctuation field was taken to be real. Now, of course, this reality condition is because the field was considered real. If it was complex, then of course you don't have to worry about something like this. Okay. Then after having computed this, one can compute the two-point function using this formula, the quadratic formula of action. Okay. And once you compute that, the real space two-point function can be obtained by doing the inverse Fourier transform. Okay, so that is the general procedure for computing the real space correlation function. Okay, so one of the things that we had seen last time was that, like, if you look at the Fourier transform of quantity like p squared plus 1 in the denominator, then that kind of quantity would be written in terms of a function which depends only on the magnitude of the distance between the two insertions and not on the angle, simply because this, in the momentum space, this quantity is rotationally invariant, and therefore the corresponding function should also be rotationally invariant. Okay. Fine. So after having done that, we found that we could kind of determine the critical exponent nu by just studying this behavior of the system by extracting out the power law dependence, and then we said that psi goes proportional to 1 over m and nu is equal to half. Okay. Fine. Now, this behavior of the two-point function, which is on purely power law, happens only in the vicinity of the critical point, because if you are away from the critical point, then you have this this mass term sitting around in the two-point function, and that is the one which gives rise to exponential damping factor. But in the neighborhood of the critical point, this term vanishes, and therefore the two-point function really goes as 1 over k squared in the Fourier space, and whose Fourier transform in d dimension gives you mod x to the d minus 2. Okay. Now, of course, in our study of critical phenomena, we expected two-point function to have a factor which goes at 1 over mod x to the d minus 2 plus eta, but the answer in Landau-Ginsburg theory is precisely d minus 2, implying that eta should be 0, which is precisely the mean field exponent. Okay. Fine. So let me skip this other delta critical exponent and try to go ahead with the conclusions that we had drawn from the Landau-Ginsburg model. And the main conclusion that we had drawn was that it produces all the mean field critical exponents, and therefore it also carries the same problems that the mean field critical exponents had. Namely, all the critical exponents were independent of dimension. Okay, so therefore, explicit dimension dependent behavior of the critical exponent is not something which Landau-Ginsburg model would have picked up. Okay. On the other hand, experimental data clearly shows that two-dimensional Ising model critical exponents are different from three-dimensional Ising model critical exponents, and so on. Okay, so clearly that dependence is not born out of the Landau-Ginsburg model. Okay. Now, in the mean field theory, we basically claimed that this J times SI dot Sj type term can be written as average value of one of the spins and the spin which is coupled to the average magnetization generated by a stall spin. Okay, so that is the kind of interaction that we talked about. The last piece, which is Sj minus average Sj, is something that we would have called fluctuation. Okay, so we throw this part out, and mean field theory just concentrates on the first part, saying that every spin sees the average field generated by all other spins. Okay, now this computation of uh, uh, in mean field theory, of course, was not in consonance with the experimental results. So one of the things that we could ask is that, like, is this a valid procedure at all? Okay, is mean field theory approximation a good thing to do? Okay, and one way to kind of figure that out is to define certain criteria to determine whether mean field results are sensible, reliable, stable, or not. Okay, so that is uh, that is the method that one would like to set up first, and then ask under what circumstances would a particular description be reliable. Okay, now one of the things that we could do is to look for the error in the computation uh, with respect to, say, a mean field computation. Okay, so the error is something which would look like this: that what you're doing is that, like, you're trying to find out the average uh, value within the mean field approximation. So that would be just average of SI times average of SJ, whereas the real result would in fact have average of SI SJ minus the disconnected piece. Okay, so in fact the numerator of this error function, not I shouldn't use the word error function, of this error is actually a connected part of the 2-point function that we had studied earlier. Okay, on the other hand, the denominator is a square of the order parameter, because average value of SI is just the order parameter of the system. Okay, fine. So this error is actually usually referred to as the average difference between the two expressions. That is the way one refers to this kind of error estimation. Okay, and this expression, therefore, as I said, the upper part is a 2-point function. So therefore, E can in fact be written as the average value of the Green's function divided by the order parameter square. Okay, where R is, of course, distance between the two sides, SI and SJ. Okay, fine. Now the statement is that the mean field approximation is correct and self-consistent if the error is small. Okay, so we want to ask a question: under what circumstances would the error be small? Okay, now of course let's first try to see what it means, and then we'll try to see whether this is the correct criteria or not. Okay, but that is what we want to know. Okay, as to if the disconnected if the connected 2-point function, okay, is small compared to the value of the order parameter, then you would say that the mean field approximation is valid. Okay, so that is the criteria. Okay, so this statement, E much less than 1, is equivalent to the statement that the fluctuations about the mean field are small compared to the magnitude of mean field itself. Okay, on the other hand, if E is of the order 1 or larger, then clearly the mean field theory is not reliable, and the fluctuations would overwhelm the mean field and in fact destabilize the mean field value. Okay, and in that case, of course, saying that the dominant contribution to the action or the energy functional comes from mean field is clearly not correct. Okay. Fine. So suppose we are in the deep ordered phase. That means we are, like, well below the critical temperature Tc. Okay, if the temperature is much smaller, in that case, the 2-point function, which we denote by GR, has a significant amplitude only if the R is of the order of the correlation length. Okay, and that is because so to understand that, let's go back a little. Yeah, this is enough, or this is also fine. Yeah, that what we notice is that uh, that the mean field has mass both for t greater than Tc and t less than Tc. Okay, so therefore, uh, if you are deep into the ordered phase, then the uh, then the order parameter has some average value, and the fluctuation about that would have mass. Okay, and if they would have mass, then the correlation function would be damped exponentially. Okay, so its size is kind of roughly determined by the size over which the correlation function has fallen by a factor of e. Okay. Okay. So that scale over which the correlation function falls by a factor of e is roughly the correlation length. Okay. So uh, the 2-point function would have significant contribution only if R is of the order of psi. Okay. So what we'll do is, we had computed 2-point function already in kind of some kind of operator formulation. What we'll do is do it the same thing in the path integral method. Okay. It is instructive in the sense that, like, one learns as to how to do these kind of computations using the path integral techniques. That is one aspect of it. Second aspect of it is that, many times operator formalism may be tricky, but because the action is more complicated and maybe even constrained, but path integral formulation is often much more convenient to deal with. Okay. So let's first write down the partition function in the presence of external source. Okay. Now, if you do that, then you have Q, which is the partition function of the theory, obtained by doing the integral over phi, where phi takes arbitrary value, uh, arbitrary real value, and uh, this integral is weighted by the action of the theory. So it is e to the minus s is a weight factor. Okay. The additional term, which is integral ddx h times phi, is the external source coupling to the Landau-Ginsburg field. Okay. Now, to do this, to do any computation in path integral formulation, we need to use various techniques, and one of the important techniques to kind of use in path integral is what is called the functional differentiation. So let's try to understand this definition of functional differentiation. So so let f phi x be a functional of phi x. Okay, that means, by functional I mean that, if you give me a function phi of x, then the functional returns me a number. Okay, that is what one means by f being a functional. Okay, so we define the functional derivative of f, which is a function of phi, in the following way: delta f by delta phi is given by limit epsilon going to 0 f so it's a function of phi with its argument shifted by epsilon. Okay, so we do that, and just a second. So we want its argument shifted by epsilon. Sorry, I have a typo here. I don't want this bracket to close here. I want the bracket to close. It's not the x which is shifted. It is the phi which is shifted. It's a bad typo actually. Just give me a second. Sorry, it's a bad typo because it means completely different thing from what I want to say. So it's not that the x is changed, but it's the argument of f which is shifted. Okay, so it will correct soon, but let's proceed. So we define the functional derivative of a functional f, which is a function of phi by delta f by delta phi x to be, yeah, now it's corrected. Limit epsilon going to 0 f of phi x plus epsilon times the delta function minus f of phi divided by epsilon. Okay, so this is how one defines the functional differentiation of this thing of a functional f. Okay, the best way to do this is to, in fact, discretize the space. Okay, that means instead of taking x to be continuum, you take x to be discrete quantity, and if you take x to be discrete quantity, then phi of x can be written as phi at, x vector can be written as x1, x2, x3. Then you can think of phi at x1, x2, x3 as kind of subscript on phi, and then it becomes, then this functional actually becomes function of the quantities defined at every space-time point. So it's kind of a easier definition that way. Okay, and then of course you take, besides taking epsilon to 0 limit, you also have to take a continuum limit to convert the ordinary differentiation into a functional differentiation. Okay, I have it in my QFT2 notes, but not here. So that would take much more time somehow. Okay, but if you want, I can kind of upload those. Okay. Okay, so but coming back to this thing, so use this definition and you can do this following exercises, which are not very difficult. Okay, first thing is that that you differentiate a function, okay, with respect to itself defined at a different location. So delta phi x prime by delta phi x, and that quantity would be given by delta x minus x prime. That is not a very difficult thing to check because you can just expand, Taylor expand this quantity. This term would cancel. You get a delta function piece. This functional is just phi itself, so therefore it's kind of easy. You get a delta function directly by doing this. Okay. Once you get this one, then you can plug that up here and show that if this quantity is not just a function but integrated quantity, then it will give you 1 because this delta function would sit inside and it will give you the answer 1. Okay. The other thing that you can do is take delta phi x of a quantity like this, which is the kind of quantity that appears in the Lagrangian in some kind of kinetic type terms. Okay, and you can show that you need to do an integration by parts to arrive at this result. Okay, so if you kind of convince yourself that these results work out, it would be useful for doing manipulations in the path integral formulation. Okay, fine. Now, we want to use these methods to compute certain things. And the first thing that we want to compute is what's called a response function. And that is defined as the functional derivative of the free energy of the Landau-Ginsburg model. Now, what we have done so far is written down the partition function of the Landau-Ginsburg model in the presence of external source. To take the free energy, of course, you will have to take a logarithm of this object. Okay. So here is the free energy defined as log of the partition function in the presence of some external source. Okay, and the response function is basically a derivative of the free energy with respect to the external stimulus, and which is in the Ising-like model would be the magnetic field. Okay, if you want to so that is one point function, but this is what we would actually call the order parameter. And if the order parameter has non-zero expectation value, then we would say that we are in an ordered state. And if it has vanishing expectation value, then we would say we are in the disordered state. Okay, and in the Ising model language, non-zero value would mean non-zero magnetization, and zero value means zero magnetization, and therefore you are in a paramagnetic state, whereas you are in the ferromagnetic state in the case of non-zero magnetization. Okay, so this quantity delta F by delta Hx is kind of easy to compute, because you think of Q written as an integral over all values of phi, exponential of minus s minus h times phi integrated over the whole space. Okay, so this bracket starts here and ends here. Everything is inside the bracket. S is written with a square bracket phi because that is the definition of functional. Functional is typically written with its argument written inside the square bracket, and its argument typically is a function, and therefore it is that function is written in with its argument written in parentheses. Okay, so therefore this square bracket is different from this square bracket. Okay, maybe I should have drawn a curly bracket here. That would have been kind of easier. But yeah, so now you have Q written like this. Okay, your F, which is the free energy that we are looking at. Okay, that free energy is log of Q. So you are taking log of this quantity. And now if you differentiate F with respect to H, okay, now notice one thing, that look at all these expressions and you notice that if you have an integral and if you do a differentiation, then the integral goes away. Okay, and that is because when you do a differentiation, it gives you a delta function, and the delta function is soaked up by carrying out that integral, and therefore you are not left with that integral. Okay, so your partition function contains integral d dx h times phi. So if you take delta h of Q, okay, then it will just bring down phi of x and no integral. Okay, fine. Now, of course, we are not doing delta Q, but we are doing delta F. But that is not a problem, because delta F means derivative of log of Q. That means 1 over Q times delta H of Q. Okay. So derivative of Q with respect to H divided by Q. That's what it will give. Okay. But that quantity would be just phi of x and no integral involved anywhere. Okay, because after functional differentiation with respect to h, whatever delta function you get will be soaked up by this integral and just gives you phi. Okay, so the reason why I'm kind of belaboring this particular point is that if you want to compute multi-point correlation function, okay, this is a one-point function, which is what is called a response function. But if you want to compute two-point function, all you have to do is to differentiate twice. Okay, so in that sense, this method of doing computation of correlation functions in quantum field theory is much more efficient, simply because in the path integral formulation, all you have to do is to do a functional derivative of the log of the partition function. Okay, and notice one thing, that because it is the log of the partition function, when you differentiate, you have derivatives of the partition function sitting in the numerator divided by the powers of partition function sitting in the denominator. Okay, and therefore these correlation functions are correctly normalized correlation functions naturally. Okay, you don't have to do any extra work over this. Okay, so coming back to the point of studying correlation function, the 2-point function would be obtained by just differentiating the free energy with respect to the external source twice. Okay, fine. Now the subscript C actually stands for the statement that this 2-point function is actually connected. So by connected, I mean it is like in the discrete form, it would be like this: that SI Sj average value minus SI average Sj average. Okay, so the disconnected piece inside SI Sj average is subtracted out. So whatever is the numerator here is only the connected part of the 2-point function. Okay, so if you use the free energy description, then you naturally end up with the connected correlation function. Okay, if you don't do it this way, if you don't write down log of Q but just differentiate Q, then you will actually get 2-point functions which could also contain disconnected pieces. Okay, fine. But recall that this is the order parameter. Let's go back to the Ising model description. The order parameter is magnetization. Okay, and we want to study, so maybe I should not have skipped that part. Okay, let it be. Yeah, doesn't matter really. So this is like magnetization in the Ising model. And if you want to ask what is the magnetic susceptibility, then you want to ask a question: how does the magnetization change as you change the external stimulus, as you change the external magnetic field? Okay, so therefore, rate of change of this value, this expectation value of the order parameter with respect to the external stimulus is what you would call the susceptibility. Okay, so therefore, it should be defined as susceptibility is rate of change of the average expectation value of the order parameter with respect to change in the external stimulus. Okay, but notice that if you look at this expression, then this expression already has this first piece, which is the definition of the order parameter, and the second piece is just the rate of change of that order parameter. Okay, and therefore the susceptibility is related to 2-point function. Okay, is that fine? Okay, fine. So one of the things which is not immediately manifest here, partly because we have done some sloppy thing, well, not sloppy, but some trick thing to kind of remember we had a partition function which was written as trace e to the minus beta h kind of stuff, and we said that we can redefine some quantities and soak up beta inside. Okay, and then we kind of wrote down Euclidean action functional instead of writing the Hamiltonian. But usually it is a good idea to keep that beta, because there is a kind of small normalization issue between the susceptibility factor versus the 2-point function, and that is the susceptibility is related to 2-point function through the factor of 1 by kt. Okay, so although these expressions look the same, there is a factor of 1 by kt between the 2-point function and the susceptibility. Okay, one has to just do a little careful calculation to get it right. Okay, fine. So one could kind of study this in Fourier space. Okay, and in the Fourier space, it would look like chi tilde of k is related to beta times g tilde of k. Okay, the susceptibility that we have been talking about, say in the mean field approximation and so on, is what is called the static susceptibility. Okay, it does not depend on the fluctuation because our mean field is supposed to be spatially uniform. If something is spatially uniform, then clearly the momentum number, the wave number should be zero, because there is no spatial dependence of that. So to determine that static susceptibility, what we need to do is to take k going to zero limit of this expression. Okay, and if you want to do that, then remember that you start with this function and write down g tilde as a Fourier transform of that. Okay, but if you want to take k going to zero limit, then the Fourier transform would have g of x times e to the I k dot x kind of piece. But if you are taking k equals zero, you just have this quantity. So chi tilde k is just the integral of the g over the entire space. Okay, that is how you would get the static susceptibility from the 2-point function. Okay, so let's try to compute this 2-point function. Okay, and that is usually done in 2 steps. Okay, first step is to extremize the Landau-Ginsberg energy functional. Okay, and that extremization, of course, would give you equation of motion. Okay, and then the second step would be to differentiate with respect to the external source to obtain the 2-point function. Okay, so that is the way one would arrive at the 2-point function. Okay, so here is the equation of motion. We had the action which was grad phi whole squared plus a times phi, a by 2 times phi squared plus g by 4 times phi cube minus h times phi kind of stuff. And if you use equation of motion, you get something like this. Okay. So now we will do the second step. This is just variational principle to arrive at this statement. Okay. The next step is to vary the external source and ask how this how it affects the equation of motion. Okay. Now, of course, we want to set that also to zero. Okay. So we want to ask how we would get this. Okay. So of course, if you change the external external stimulus, then your order parameter also changes. Okay, that is the statement about the susceptibility. Remember? Okay, so therefore, it is not that like when you take delta delta h, it kind of kills this term and just acts on that. That's not true. It actually acts on all of them because everybody is affected by the external stimulus. Okay, so you take delta h of phi, delta h of this phi, and delta h of this phi cube. Okay, and if you do that, then you would see that every time you take delta h of phi, that is related to the susceptibility through this formula. Okay, so from this we would derive a differential equation satisfied by the susceptibility. Okay, so this will give you a susceptibility factor. This will give you a susceptibility factor. This will give you a 3 times phi squared, okay, times the susceptibility. And the last piece of delta h acting on this would give you a delta function, which is pulled out on the right hand side of this equation. Okay. Now, if you stare at it, you can easily see that this is pretty much like the Green's function equation. Okay, and that is how the 2-point function is also computed. So it is no surprise that the susceptibility equation of motion is related to the 2-point function of the system. Okay. Any questions here? Hello? Connected. Hello?
Yeah, you're connected.
Oh yeah, connected. No. Oh, okay. Okay. So um, yeah. So using basically these relations, we see the relation between the susceptibility and the two-point function. Okay. Uh, yeah. So fine. Uh, now, of course, if you are working at temperatures larger than Tc, then the average value of the order parameter is 0. So therefore, this term is not going to contribute, and you are reduced to this equation. Okay, and because there is a relation between chi and two-point function, which is related to 1 by kt, I will just pull this both one constant times temperature on the right hand side. Okay, now we could define uh, xi greater, that means for t greater than tc, to be a times t minus tc to the minus half. And if we do that, then uh, we can kind of try to solve this equation in terms of this xi greater, which is just the correlation length of the system. Okay. Uh, if xi is less than, if t is less than tc, then of course the phi is non-zero, and so we'll have to substitute that phi value, which is uh, given by this factor. A is what we are written as minus a by g to the half, but a itself is a0 into t minus tc. So we can take this quantity and plug it into this expression and simplify. Okay, you can see that a lot of simplification would occur because phi squared will have a g in the denominator and a t minus tc in the numerator. So you can kind of get rid of this g. The factor of 3 versus factor of 1 would kind of give you a new number sitting around. Okay, so you get xi less is equal to minus 2 times a naught times t minus tc to the minus half. Okay, and this factor of 2 difference between the two is something we had observed earlier also. Just to kind of show it, you can just scroll back, that the masses are related by a by 2 versus a. Okay, this minus sign is of course because for t less than tc this quantity is negative. Okay, fine. So we define the correlation length uh, for t greater than tc and t less than tc, and expectedly they have a relative sign and a factor of 2 between them. Okay, but the power in both cases is minus half, which is what the mean field expression that you would have got. Our equation therefore would look like this, irrespective of whether xi is greater or xi is less. The explicit value of xi for t greater than tc and t less than tc would be different, but the equation would look the same. So we can solve this equation. In the Fourier space, the answer would look like kbt upon k squared minus xi to the minus 2. Okay, fine. So I suppose this is fine, right? Green's function technique you must have learned mm, both in math method as well as in electrodynamics, right?
Yeah,
Yeah,
we read that. Yeah.
yeah. Okay, good. So you get the solution in Fourier space like this, and we know that when t is equal to tc, from this expression also you can see when t is equal to tc, xi is going to be infinite. Okay, and if xi becomes infinite, then xi to the minus 2 is 0, and therefore you have just g tilde going as 1 over k squared. Okay, and if it goes as 1 over k squared, then you can do its inverse Fourier transform and write down the real space Green's function, which will go as 1 over r to the t minus 2. Okay, and we know that the behavior would have, critical behavior should have been 1 over r to the t minus 2 plus eta. Okay, but given that we get this answer, tells you that eta would be 0. Okay, this we need not have to come here, we would have seen it right there, in fact. Okay, fine. So of course, to get static susceptibility, we actually have to take k to 0 limit of the two-point function, and in that case, you set k equals 0, xi goes and sits in the numerator, and therefore chi is proportional to xi squared. Okay, so that would be the behavior that we would get. Okay, fine. Now, if you want to keep xi to be non-zero, that means you are not at t equals Tc, but at arbitrary temperature, then you can in fact do the inverse Fourier transform, and the answer is something like this. Okay, it is some numerical factor 2 pi to the minus d by 2 times r by xi to the d minus 2 by 2 minus d minus 2 by 2 times the modified Bessel function k with the argument r by z and index d minus 2 by 2. Okay, the function k actually has a behavior that it is exponentially damped for large r, and it is power law for small r. In other words, the differential equation that it satisfies has regular singularity at small r and irregular singularity at large r. Okay, so these are the kind of behaviors that the modified Bessel function would exhibit. Okay, so Kn would go as 1 over x to the half times exponential of minus x. So it is exponential fall. Okay, that is for large x. For small x, it goes as x by 2 to the minus n. Okay, so that is the small x behavior of the solution. And the third case is when the argument n is equal to 0. Okay, and if the n is equal to 0, then you would have thought that it would have no x dependence, but that's not the case. It actually has a logarithmic behavior. Okay, and so this logarithmic behavior tells you that the Green's function with k equals 0 would violate the scaling law. Okay, but now going back to this 2-point function, you will notice that kn values that we have written down are valid. I mean, non-zero n values are valid when d is has a different value compared to, say, d is equal to 2. Okay, but if d is equal to 2, then in that case you actually get a logarithmic behavior of the system. Okay, in fact, if you study the system a little more carefully in say d is equal to 4 for some other behavior, you get similar kind of expressions, and you again see that there's a logarithmic violation. We'll come to that little later. Okay, but what this tells you is that when this argument goes to 0, the system actually has scaling violation. Okay, so it's not like we would have recovered, we would have killed all this exponential behavior and would have had a good behavior, but that's not the case. Okay, but this is of course small x behavior of the system. Okay, which is what we would call the ultraviolet behavior of the system, small distance physics. Okay, fine. So if you combine all this, then the real space expression for this Green's function, take this factor and take these behaviors into account, plug them up here and write down the Green's function, it takes the form something like this. Okay, so there is some numerical factor sitting around, which is kind of part of all these various integrations and pi's and factors sitting around. There is a KBT factor, which is kind of going around with the G all the time. So that is the factor which is sitting up here. And then you get r to the d minus 2 by 2 in the denominator, which is the effect of this computation here. Okay, and e to the minus r by c is the effect which comes from here, where k has argument r by c. So if you put r by c, you get exponential minus r by c factor. Okay, which is that. Okay, fine. Now, So this is how the two-point correlation functions are going to look like. One can, of course, deduce susceptibility dependence right from here, because the difference between G and susceptibility was just the factor of KBT. Okay, but to be a little more precise, there is one more additional dimension-dependent factor sitting around here, which we had actually ignored in our computation. Well, maybe not ignored, but what we did was that we said that like we can scale the fields appropriately to soak up that factor. Okay. But what we need to do is to actually just kind of go back and take a look at what that factor is, partly because it is dimension dependent and partly because it should give some relevant kind of perspective to the error that we are trying to compute. Okay, so let's go back to the original problem, and let me write that original problem in a little different form using mean field theory. The original value was of the Gibbs free energy was written in terms of Ji, J, Si, J, but in mean field theory we are going to use average description, and average description of Si's and Hj's would be Mi and Mj's, which are the order parameters. Plus you have other terms like, if you have external magnetic field and terms like that, which are not of much importance. I just put ellipses there. Okay. Now what we had done was we took continuum limit of this particular term, okay, to arrive at some kinetic energy like term. Okay. So to do that, what we did was the following, that we said that this sum over nearest neighbors, for example, can be written as sum over all the local values of order parameters within a small open ball defined by R. Okay, and we compute this quantity by writing M I plus delta, where I is the location at which the M is defined, and you look at the difference of that divided by the lattice spacing squared minus the sum of those things times lattice spacing squared. Okay. Now, if you look at this term, then you can see that the first term actually is like a gradient of the order parameter times, of course, the small incremental distances that are used for defining the difference equation that we have. Okay. Fine. So what we want to do is to take continuum limit of it. That means we want to take the lattice size going to lattice size going to 0, and in that limit, this particular sum gets converted into a d-dimensional integral divided by, of course, the size of the unit cell, which is a to the d, which is the one which carries the information about the lattice. Okay, and the factors come out in the following fashion. The factor of A comes out and soaks up this A. The factor of delta, which comes out through this sum, actually contributes the factor R squared here. Okay, the factor of delta squared coming out. Okay, so what we get is an expression something like this, with J times this A gets cancelled with this delta contributing R squared here, and this Z tells you what is the total number of neighbors, which is what is called the coordination number of the lattice. Okay, so what we find is that the kinetic term doesn't have canonical normalization like half grad M squared, but it has some factor like this sitting around. Okay, and that factor is like J squared K, R squared times J times Z upon A to the D. Okay, now if you recall that J times Z is the quantity that we had shown earlier to be proportional to the KB times TC. Okay, so what we find is that the normalization of the kinetic term is so this is the relation we had derived long time ago. So, so what we find that the normalization of the kinetic term is actually a factor like that. Okay, so we need to kind of take that factor into account while studying this the error that one is looking at. Okay, so so the error actually takes the form which is remember there is a Green's function in the numerator. Maybe let me just scroll back. The Green's function in the numerator and phi squared in the denominator, phi m squared in the denominator. So yeah. So the Green's function has a dependence r to the 2 minus d, and then there is this normalization factor which gives coming from here, which gives you a to the d upon r squared, r squared times tc. The factor kb cancels with the numerator factor kb times kbt, which was there with the Green's function, and you get e to be a function of this. Okay, which you can massage it to write down t by tc times a upon r to the d. But a upon r to the d is same as 1 over the coordination number to the d, right? Because a is the lattice height, r is the size over which the interactions takes place. So r by a is the coordination number z. Okay, so the error is t by tc times 1 over z to the d. Okay, so if you are considering temperatures T much less than Tc, okay, then in that case, of course, T by Tc is small. Okay, even if the coordination number is of order 1, the quantity kind of z to the d is not going to affect much, and you will find that the E is smaller than 1. Okay, and therefore you will conclude that the mean field theory is consistent if you are well below the transition temperature. Okay, now notice one thing, that we are making a statement about mean field theory as a tool, but not as a tool to determine critical exponent, because we are way below the critical temperature. Okay, so you can do mean field theory calculation using Landau-Ginsburg theory at any stage of the system. You may be well into the ordered phase, well below the critical temperature. Mean field theory would work, in fact, would work more reliably because the error is small. Okay, of course, because you are doing mean field theory in deep ordered phase, you won't be able to get critical exponents. Okay, and therefore the critical exponents that we have obtained using mean field or Landau-Ginsburg formulation are not going to be correct. Okay, so that is that needs to be kept in mind. Okay, but if you are in this regime, then the error is small, and therefore mean field results are reliable. Okay. On the other hand, if you take T close to Tc, then in that case, the region of influence of the fundamental interaction or the basic model is much smaller than the correlation rate. Okay, and the order parameter is not constant, but depends on temperature in a very specific fashion. It goes as T minus Tc to the 2 beta. Okay, so if you substitute all that, oh sorry, I should have written phi m squared. It goes as T minus Tc to the 2 beta. Okay, so if you take this into account, then you get the result, which is not this. Okay, but it goes as 1 over T minus Tc to the 2 beta times A by R to the D. Okay, now you see that, like, as you go closer and closer to the Tc, the error diverges. Okay, and that essentially means that although the mean field theory formalism is valid well below the critical temperature, it fails when you are close to critical temperature. Okay, so that is how this error computation tells you what is the reliability of the Landau-Ginsburg formulation in a setup where the system undergoes phase transition. Okay. Fine. Now, of course, one could kind of save this situation. So if P minus TC uh, is larger than the coordination number. Okay. If that is the case, then we could still manage to keep E small. Okay. And therefore, mean field theory could be valid. Okay. But if T minus Tc is greater than the coordination number, then you are still sufficiently far away from the critical temperature, and therefore mean field may make sense, but mean field may not be able to capture the critical behavior of the system. Okay. So that is how this analysis of error in uh, computation of Landau-Ginsburg formulation of mean field goes. Okay. Now, let me kind of talk about the Ginsberg criteria, and it's an important criteria because this error that we have computed is a bit sloppy. Okay, we need to be a little more careful about our computation. Okay, particularly because Landau-Ginsburg formulation is really a mean field theory computation, and therefore we have to ensure that we should be talking about quantities on an average and not the quantities themselves. Okay, so therefore therefore Ginsberg defined a new criteria, and to define that new criteria, he said that, like, one should look at the correlation function over a certain region over which the correlation function takes a significant value. If you are studying a region which is much larger than the correlation length, then actually the fluctuations that one is studying are uncorrelated, because if the correlations are falling exponentially fast. So if your region is like, say 10 times larger than the average size of the correlation length, then far separated domains have essentially independent fluctuations. Such fluctuations are called uncorrelated fluctuations. Okay, so so therefore Ginsberg defined the criteria saying that, like, you concentrate only on a region over which you have. Gee, I forgot to close the thing here. Uh, so he defined the criteria which says that, like, you integrate over a region over which the correlations are correlated. Okay, and don't integrate over a region over which the correlations are not correlated. Okay, so therefore this integral that is involved here is integral over a volume defined by the correlation length to the d. Okay, now of course correlation length itself is a function of temperature. Remember, like, as T goes to Tc, correlation length diverges. Clearly implies that correlation length itself should be a function of temperature. Okay. So therefore, what is the volume that one is looking at depends upon at what temperature are you trying to study this particular system. Okay. Now, recall for T less than Tc, the average value of the order parameters is T minus Tc to the half. Okay. And the correlation length goes as T minus Tc minus half. Okay. The other thing that we already know are that the integrated value of GR, the 2-point function, is the KBT times the static susceptibility of the system. And the static susceptibility was computed in mean field approximation, and that goes as 1 over T minus Tc. Okay. So what we can do is that we can take all these things into account and and try to kind of evaluate the Ginsberg criteria using all this information. Okay. Now, besides these, even if you are in a uniform phase, phi is not a function of space, but it is a function of temperature. Okay, and therefore we would like to take that factor into account, and phi m squared goes as T minus Tc. Okay, so if you try to integrate phi m squared, which is what is the quantity which is sitting in the denominator of the Ginsberg criteria, that would give you xi to the d times T minus Tc. Okay, with psi to the d using this behavior can be written as t minus tc to the minus d by 2. So the whole expression would be t minus tc to the 1 minus d by 2 times some psi naught to the d, which is some overall factor sitting around. Okay, so what we'll do is we'll take all these fellows expressions and put them back into this computation. Okay, uh, this is something we already know. Integral of gr is kbtc divided by the static behavior of the static susceptibility. Okay. Okay. So let's put all this together and we get this result. Okay. Uh, the the numerator, which is the integral of the 2-point function over a single domain. By that I mean a domain over which the order parameter is correlated. Okay, that gives you kbtc upon t minus tc. Okay, that is the factor coming from this integral. And the denominator piece, which is integral of phi m squared, okay, which gives you t minus tc to the 1 minus d by 2 times xi naught to the d, okay, which gives you a factor which is xi naught to the minus d, because this is in the denominator, times t minus tc to the d by 2 minus 1. Okay. So combining that gives you 1 over t minus tc to the 2 minus d by 2. Okay. So that is what is the result that you would get for the Ginsberg criteria. That is that EG would be something like this. Okay. Fine. So now we want to say argue that EG would be small, and therefore the mean field theory is reliable if t minus tc to the 4 minus d by 2, that is just 2 minus d by 2 written as 4 minus d whole divided by 2. Okay, if this quantity is larger than kbtc upon psi naught to the d. Okay, if that is the case, then the Ginsberg parameters or Ginsberg criteria would be satisfied. Okay. Fine. Now, if you are in the neighborhood of a critical point, then typically t minus tc is less than kbtc upon xi naught to the d. Okay, and as a result, the fluctuations would dominate. Okay, and in that case, Eg is much greater than 1, and therefore the mean field theory will not be applicable, and consequently the Landau-Ginsberg theory is also not applicable. Okay, so this still tells us that close to the critical point, the Landau-Ginsberg theory may not be applicable. Okay, but we need to be a little more careful in trying to understand this system, because the Ginsberg criteria, unlike the error criteria, is explicitly dimension dependent. Okay, there is a factor of d sitting around in this expression, and you clearly see that if d is greater than 4, then this Ginsberg criteria will be always satisfied. Okay, fine. So what this implies is that if d is 4 or less, then we would have had this hurdle that t minus tc is less than kbtc upon xi naught to the d, and therefore fluctuations would dominate in the neighborhood of critical point. But if you are in the situation where d is greater than 4, then this hurdle is not going to be a trouble, because when d is greater than 4, the role is reversed here. Okay, and because of this role reversal, you find that even in the neighborhood of critical point, the Ginsberg criteria would be satisfied if d is greater than 4. Okay, is that fine?
Yes, sir, fine.
Okay, so that would tell us that the Landau-Ginsberg theory would give you a correct critical exponents if the dimension of the system is greater than 4. Okay, so far we were thinking that mean field theory was not good, but now we have figured out that mean field theory would be a good description if the system that we are studying is defined in dimension d greater than 4. Okay, now if you really go back and check the table that we have written down of critical exponents, then and its comparison with mean field theory, then you will find that the mean field theory disagreed with two-dimensional Ising model more than it disagreed with three-dimensional Ising model. Okay, so if you try to study, say, Ising model in 5 dimensions, then 5-dimensional Ising model results would be in agreement with the mean field theory computation. Okay, that is what this statement corresponds to. Okay, that Landau-Ginsberg description of would give you correct critical exponents if the dimension of the system is greater than 4. Okay. It also tells us from this expression that the Ginsberg criteria would not be satisfied for d less than 4 in the neighborhood of critical point. Okay, Ginsberg criteria would still be satisfied if t minus tc is a large number, it's far away from the critical point. But in the neighborhood of the critical point, Ginsberg criteria will not be satisfied if d is less than 4, and therefore the mean field theory will not give you correct critical exponent, and that is something we have already noticed, particularly within the Ising universality class. Okay, fine. The final case is taking d is equal to 4. Okay, and d is equal to 4. This factor just cancels out, and therefore you get t minus tc to the 0th power, and in that case you would think that you may still kind of barely make it in this particular setup, but that's not true because there is a logarithmic scaling violation in the system, and as soon as you get a logarithmic piece in your correlation functions, it will invalidate the Landau-Ginsberg theory, because Landau-Ginsberg theory implicitly assumes that in the neighborhood of critical point, you would always have power law behavior of the system. Okay. So I think I'll stop at this point. We will kind of discuss aspects of Landau-Ginsberg theory in the next class, and probably generalization of that. Okay, any questions?